Great pleasure to introduce Vittorio Tornielli from ESA in the Netherlands, who's going to present us on some of the aspects of the work they're doing in the Space Agency on additive manufacturing. So over to you, Vittorio.
Hi, thank you very much. Thank you for the introduction. I hope that you can hear me. So I hope you can see the presentation. Today I'm going to give you an overview of additive manufacturing for RF passive components in space application. My name is Vittorio Tornielli. I'm a microwave engineer and at the radio frequency equipment and technology section of ESA ESTEC. And this presentation is divided into two parts. I'm mainly concentrated on RF passive components, while in the second part I will be joined by my colleague Marten van der Vorst from the antenna section. I don't know if Marten wants to introduce yourself.
So thank you indeed. So first of all, thanks for having us to present the work that we do indeed in the space domain. So indeed, I will do the second part, mainly focusing on antennas. So yeah, please go ahead.
Yeah, thank you. So basically, I don't know how many people here are familiar with RF components, and here we want really to give an overview about what are the components that we are interested in and how we can use additive manufacturing to solve a number of challenges that we face on space technologies. So let's say that in standard conditions, what do we have? We have kind of RF components. In my case, as I said, my interest is about passive equipment, RF microwave equipment. What we see here, we have two. We have on the top left, we have a filter. This filter is made by the aluminum through normal CNC manufacturing. And here in the yellow box, what's happened? Yeah, in the yellow box we see is the process. So we start from a block of aluminum, and then we are going to use milling machine to say subtract. It's a subtract manufacturing. So we are going to remove the part that we want to have empty, and then we make several parts, like here on the top left is a filter, like the main part, and then there is a lid put on top. And here you see all the mounting screws or fasteners that you need. Here in the top center, we have an hybrid coupler that is also a filter. Here is the same process. So we have a main part here on displayed on the right, and then on top we are going to have a lid. So the question is, what about if we have kind of a more complex structure? What are the benefits that additive manufacturing can bring to us? So here is an example of a very complex 3D structure. On the left side, you see what we are going to design. So typically, microwave engineer designs the vacuum part, so the part that is hollow, that is empty, filled by air on Earth, but empty cavity in space. And we want to make this. We want to manufacture this part as a real component. On in normal conditions, you can see on the top right, here we're starting from a monoblock of aluminum, and we're designing all the internal cavities, and then we had to include 4 leads plus all the mounting screws. And here on the bottom right, you see the final component. As we have now, we have tried to do the same exercise, but instead using additive manufacturing. Here we see the real benefit. So we were able to manufacture a monoblock, no mounting screws. Everything is based on a single component. This is much lighter and much easier to do, and also it reduces a lot the times for integration, assembly, and testing. So we can do kind of a very complex structures in a much simpler way. Additive manufacturing can be very useful for us, not only for say easing the manufacturing process or reducing the cost or reducing, say, the time to make the final product, but can also be very helpful for us in order to improve the RF performances or electrical performances. So here we see a very unique design in which the resonant cavities are not done by a normal cubic or a standard square structure, but here is used a kind of a super elliptic design that can only be made with additive manufacturing. Indeed, here we have made a study for at EM level, electromagnetic level, and we studied where the currents, the maximum the currents were located. And we went there, for example, here in this blue mark here, they're pointing to with the cursor. And we went there and we modified the structure locally in order to improve and reduce the loss here. Like you can see here in this funny shape. Also, a lot of study have been devoted to the design of the coupling, so the electromagnetic coupling that there is between one cavity and the other cavity. So these are the cavities here that are circular, and these are connected through electromagnetic couplings. And as you can see here, the shape is quite complex in order to improve the RF performances, namely to provide enough bandwidth and to reduce the losses as much as possible. And you can see here that the mission was accomplished quite well. It's a good good performance from the measurement compared to the theoretical solution. Another branch that can be very interesting for us is how to use ceramic with the additive manufacturing. Why ceramic? Ceramic are a very important topic for us because for their electrical property, in particular for the epsilon R, we are able to shrink the dimensions of a normal components, a component filled with air. So the idea here is to exploit the freedom that additive manufacturing provides to have a ceramic additive manufactured ceramic part that can enhance the electrical performance. For example, here we see a C-band at 4 gigahertz micro filter in which there are here what I'm pointing here are the two resonators that are inside the filter, and what are these kind of squares are the electromagnetic couplings between two pairs of resonators, or between the resonator and the external coupling, the external port. On the bottom, we see the enclosure. Enclosure also has been made by additive manufacturing, starting from a ceramic structure, and then this has been plated, because of course we need to be plating. And this is quite remarkable because, as you can see, that the term of merit here, we have a €1 coin. So this filter is extremely compact for a C-band filter. So here we have a real advantage. Here is another example of a filter made of a transverse magnetic mode resonators. On the top left, we can really see what is the advantage in terms of the shrinking that is provided by using a ceramic material. So, for instance, the blue material that you can see here is the internal parts, the vacuum of the internal parts. Like if you have air, or if you have empty space, you can obtain the same properties for the same filter using a ceramic alumina, in this case, material, to get the same performance, but with a reduced size. So here I just wanted to show a couple of examples of filters that are using this alumina in order to provide a filter response. Here we are working X-band around 8 gigahertz, and Here are two examples of filter, one on the left side and one on the right side. Technology is the same, are different type of resonator. Here is a TM mode as well. Here the coupling here is a little bit different, but both filters need to be metallized after that. This is a little bit of a challenging indeed. The result has shown a slightly shift in frequency. Unfortunately, this is a behavior that is under investigation and still is part of the uncertainties of the process, namely the metallization and the thickness of this component. In this slide, instead, I wanted to show you how really we can have an improvement using additive manufacturing with ceramic from the point of view of the electrical performance. So we said already that the alumina can bring shrink the dimensions. So here on the left side we see the resonator with this type of L shape. This is the ceramic resonator, and this is quite smaller compared to the waveguide input and output. However, if we go on the center, we have kind of the same principle for the same resonator, but with a kind of funny shape. This has been possible to use by printing it with additive manufacturing in this case. And what is interesting is to show the frequency response on the right. So the continuous line refers to the filter on the left, while the dot and dash line refers to the response of the filter in the center. As you can see, for the continuous line, we have kind of a spike. So we have a resonance that if we want to use it in a normal condition, it is probable to have the need, the requirements to have perhaps a more complex filter or a low pass filter, so a second stage of filter in order to delay this spurious frequency. But instead, we see that we were able to cancel this spurious frequency by means of making a more complex shape of the resonator. So this is really showing the benefit of this additive manufacturing can bring to the designer as well, not only for the manufacturer side, but also for the electrical part. Another area of interest are the filters made out of plastic. So here, additive manufacturing in form of a polymer. On the top right, we see the principle of the filter. Here is a C-band filter with a 2 resonator made out of 2 mushroom type resonators. I would like to point you the attention to the line, to this kind of blue line that is connecting these 2 resonators. This is not a mechanical line. This is not a mechanical bar. This doesn't stand there for a mechanical reason, but it stands there for electrical reasons, because thanks to this line, we are able to provide a transmission 0 in the transfer function, that is namely this part here that I'm indicating. This is able to provide a more selective filter without the need of increasing the number of resonators. So making this more compact indeed. This is of great benefit because we can make this structure out of polymer, like here, and then we can metallize. Here is that there's 2-stage metallization. One is the stage of silver, then a stage of copper, and then we can obtain a device that is very compact, is very lightweight, and there's interesting RF performances. So we have plenty of benefits put into one and single component. This is my last slide from my side. So here I want to look about the future of additive manufacturing for our application of interest. And indeed, here is how to use these technologies for high frequency components. Here we're talking about the W-band waveguide filters. On the right is a filter. On the left we are a V and Q band, V and W band power splitter. And we really see that with the micro laser sintering, we are able to to make a very precise and very performance with good performance filters also these frequencies, and these frequencies are typically very challenging. So in the future we will also break the barrier to have this kind of components also at higher frequencies. So I think, Martin, it is your turn.
Yeah, okay, thanks Vittorio. So indeed I will try to keep it not too long, because I see the time is running. So we have already seen a lot of advantages of additive manufacturing for RF components. Here's just quickly a list of things, why we consider them at all for antennas. So we have, of course, less waste basically using this procedure, producing these antennas. Very important, we can have quickly products ready, so reduce time to market. Innovation, I don't think it needs explanation here. Mass reduction is very important for parts that we need to bring to space, obviously, and complexity. So next one, please. There's, of course, also reasons why not to. I mean, additive manufacturing might be beneficial for certain number of parts that will be produced. Mass production is not really the strength of additive manufacturing. We will see later as well some examples of larger parts that might be difficult to produce, at least nowadays. The process, of course, yes, needs optimization at the moment. We might have issues with surface finish and dimensional accuracy. Also, I will show something there. And then, of course, the heritage. We, of course, rely on space heritage to fly our components, and basically introducing a new manufacturing technology like additive manufacturing. Yes, it takes time to bring the right technology to the right level so that we can fly these kind of technologies in space. Next one, please. So here, this is a clear example of an antenna where you can see the benefits. So what you look at here on the left and on the right is basically a monopulse K-band antenna array, 4x4. So instead of the traditional way of producing this part, what you see on the left, it consists of 100 discrete parts that you have to put together with screws. Basically using now the metal 3D printing, they were able to make a monocoque design, so basically a single piece, reducing the lead time from 11 to 12 to 2 months. The mass reduction was 95%, and you see production costs heavily reduced, and also recurring cost. So this is clearly, yeah, a lot of advantages that we can get from additive manufacturing. Next one, please. Now I show some parts using different techniques that we consider. So these are some components that we have designed together with industry, and they were manufactured using selective laser melting or sintering, so SLM, SLS. So this produces, of course, metal parts that can easily be flown into space because it can withstand the temperatures that we need. So we see a feed horn on the left. Then you will have there's a C-band. It's a big piece, the one in blue there. That's I don't have the pointer, unfortunately. And then we have yes, exactly on the right we have a helix antenna that we use a lot for as a low gain antenna on all our satellites, basically, and then some other yes components at the bottom, all made out of aluminum. Okay, next one. This is an example of some parts that were not produced. The previous ones were produced in ESA contracts, and these are just yeah, that I found online. But the one on the left we have already seen, the 4x4 antenna array. What's also very interesting, the one below that one. So when we design a dual reflector system, so it's an antenna with a big main reflector and also a smaller sub-reflector, and then also we need to have a feed horn to feed that. So normally they're all separate parts, and then we need to put them together and make sure that the alignment is good. But in this case, they were able to produce the feed together with the sub-reflector, so it's on the left bottom. into a single piece out of metal. So you don't have, of course, you don't have the alignment problem, and you can also have the very accurate positioning between the two systems. So clear an advantage here as well, besides mass optimization, of course, that you can achieve. And then some other parts as well. You can also make array antennas, of course. I will show more in a later slide. Next one. Yes, so the parts before were produced using metal 3D printing. You've seen already before in the previous presentation polymer-based filters. So also here we have antennas that you see that are produced with stereolithography. Gives you more accurate antennas and RF components than the previous SLM, SLS methods. So for high frequency, definitely this is better. Of course, for space is difficult because you will use a polymer-based material that later on is metallized, but due to the thermal expansion, it is difficult to fly these things into space. It depends a bit on the temperature profile, of course, that we experience. On the left, you see a dual reflector antenna. I will show more on that. Then there is next to is an array antenna. This is one that is a typical antenna that could fly on an aircraft with mechanical steering. So this is a non-steered antenna, but it's just a fixed beam. And then, some other examples as well, a phased array on below and some feed cluster. One of the advantages, of course, if you use 3D printing is you just don't simply produce one, but you put multiple feeds together and you produce that as a single element, reducing the mass. And so a lot of advantages there as well. And on the right, you see the bottom. It is an antenna which is printed but not yet metallized. So of course it will also have the copper plating later on, or silver. Next one, please. Yes, some of the issues that we have to tackle. Antennas and RF components need to have high performance, at least for antennas we look at, and we require very low insertion losses. Surface roughness is one thing that is related to this. And here you can see an example of some loss measurements that were done on polymer-based materials that were copper plated. And basically on the curves that you can see there is that they can achieve quite low losses, which is good, of course, because so we can compete with traditionally produced parts. Yes. Okay. Next one, please. Another very important topic is the printing direction. The part that we see here in the green color is basically one working at low frequency C-band, so 3 to 4 gigahertz. It's a large part that hardly fits in the build volume of the printer, so you have to put it at an angle to be able to fit. But this kind of circularly symmetric structures you would prefer to print vertically, but we were not able to do that. So then the issue is, of course, when you measure the performance, you see that there was an issue with cross-polarization. And this comes due to the non-rotationally symmetric structure that was produced. So this one went through a CT scan, and based on the 3D points that were measured, we tried to have an assessment of the errors, and basically doing some kind of sensitivity analysis, you can show that indeed the errors really correspond to, they are the reason why the measurements were not so good, and we were able to reproduce them. But of course, the trick is now to find a printer with a bigger volume so that you can print this kind of structures. Okay, next one.
Martin, I'm terribly sorry to interrupt your presentation, but would it be possible to wrap it up just so we can stick to some of the time? I do apologize.
No,
it's a very interesting talk, so sorry.
No problem. This one we can skip. This one as well. So here we quickly see a leaky wave antenna, basically where you want to model the inner structure of the antenna. And Yes, this you cannot easily do with normal manufacturing. So the thing here is using additive manufacturing, you're able to modulate really the ridges inside the antenna. The performance you see measured here is quite good. So next one, please. Yes, state of the art. This is from Swiss 12, a company producing very nice hardware for space. And you can see the future really is to go into larger arrays. So you can quickly build large arrays using additive manufacturing. You don't have to do one by one. Next one. Yes, the future. So instead of only the antenna, you can also integrate the antenna on the CubeSat and then produce the part, the CubeSat together with the antenna. Some of the parts have already flown into space, and so for metal printed, this is already space qualified. For the polymer printed, this is not yet space qualified. Next one. Yes, so really the future. So instead of only sticking to producing the parts on ground, we also think of 3D printing reflectors into space. And you see on the bottom left an artist impression of that. So we bring the printer to space and directly try to produce the big 20-meter or more size reflectors. And of course, thinking about going to the moon, which is really into the future, we could take the printers up there and use base materials that we find on the moon to produce not only antennas, but housing as well. I think this was the last one. Yes. Sorry, I had to speed up a bit, but no. Okay, this was...
Thank you very much, Martin.
Part.
Okay, yeah. Thank you very much, Martin and